So I think today we're going to talk mostly about like equations of state and also energy inside of stars and maybe a little bit on how gas clouds collapse. But before we get into more of the details of that, we'll just continue along this story that astrophysics courses are trying to tell. So after you're able to describe kind of these like large scale collections of particles in space, you talk about, well, what happens when, you let gravity take over, and you talk about the interactions between gravity and pressure, and how sometimes if you have a really big gas cloud, gravity is going to contract it. But then if you've seen a little bit about the physics of gases, you know that if you have some type of volume and some type of temperature and the gas compresses, the pressure is going to go up, which is actually going to cause, the particles to move outwards. And so then there's this kind of interplay between gravity and pressure. And when does the gas actually turn into a star? What does it mean for a gas to turn into a star? Right? Actually, I think the definition is that nuclear fusion occurs. As soon as nuclear fusion occurs, then it's a star.
Doesn't nuclear fusion also occur in a protostar, or am I wrong?
I don't think so.
No.
Because when nuclear fusion starts, that's when you like hop onto the main sequence. If that doesn't happen, then you're just kind of like, there's like convection going on and just like energy transport within the gas. But like nothing's alive, essentially.
I guess, yeah, nuclear fusion kind of starts the whole process. Have we spoken about like nuclear fusion
I think we have.
in depth?
I think we have. We can get back to it though, because we're actually on this step of like in our course right now, we're learning about nuclear fusion and pre-main sequence. So what it takes for gases and how do you describe gases that have yet to become stars but are about to. And then after you talk about making a star, you get to the main sequence. And the main sequence is the longest stage that a star remains in. How do we know this? Well, you can do a little bit of mathematics about how long it takes to burn hydrogen if a star is made of mostly hydrogen versus how long it takes to burn helium and all those other elements. Or you can look into the sky and see that most of the stars in the sky are on the main sequence. Therefore, they probably are there for a very long time. We have evidence either way. After that, after you're on the main sequence, what happens when you run out of hydrogen? Well, if you have enough mass, you have enough gravity pushing into the core, you could fuse other elements, and you could start veering off of the main sequence but continuing on into the red giant phase, the red giant branch. Or if you don't have enough fuel, I guess, to keep burning, then you turn into something like a degenerate remnant star, which could be either a white dwarf or a neutron star, which we might talk about today.
Degeneracy is kind of,
actually, yeah, we will talk about that.
Yeah,
we will talk about that.
It kind of goes with
sure.
equation of state
Yeah.
and like talking about like different levels. But and what's interesting about all of this is that these gases, first of all, can also make the star. Like before we actually even go into the fusion of it and talk about the actual making of the star, this gas can also have very many different properties, right? Like the gas can either be kind of like a classical gas and kind of idealistic, and like in physics, well, we call that an ideal gas. Now there are specifics, or there are properties that an ideal gas needs to solve, but usually when we're talking about gases in like clouds, we can make a safe assumption that most of them are ideal, especially like before the whole phase of them actually going nuclear and going into the protostar and then the actual stellar phase. We can definitely assume, or at least like to a brief extent, that they are ideal.
It's not really a safe assumption, but I think it's just more for convenience.
Yeah, I don't think it's not actually an ideal gas, because there's no perfectly ideal gas in the way. I should be knowing this, but what's like the definition not the mean spacing definition, but like the other definitions. Like it has to have some temperature. Like there are certain points that kind of a gas needs to kind of like check off to be ideal. But like the biggest part of the gas being ideal is very simple. So in quantum mechanics, there's a thing called the de Broglie wavelength. Now I know I'm mispronouncing that, but I think that's the English pronunciation. So the de Broglie wavelength is every object has a de Broglie wavelength. And what's the best way to explain a de Broglie wavelength? It's basically like your quantum mechanical wavelength, right? And every gas, therefore, also in space, would also have a de Broglie wavelength.
The particles of the gas.
The particles of the gas exactly. Now, the particles of the gas are also, not obviously stuck together because they are a gas at the end of the day. So there is quite a large intermolecular spacing between them. So the question of is it ideal or is it or do we treat it a little quantum mechanically is the spacing between these particles, like the average spacing, it's called the mean spacing. So is the mean spacing between these particles greater or less than the de Broglie wavelength of these particles, of this gas, of the particles in the gas? So if the mean spacing is much greater than the de Broglie wavelength, which is usually the case when we're dealing with, these stars, or at least gases before they turn into them, we can assume it's ideal. But the moment that's no longer the case, and this can happen when the density rises, if they're really high dense regions of space, then we start treating it a little bit differently and we get a little more into quantum mechanics, and the gas is now described via, I don't know if it's described via Fermi, like fermions. It's kind of like what's the word that I'm exactly looking for? I'm forgetting the exact word that I'm looking for. But
Fermi statistics? Is that
no, Fermi. It's not Fermi statistics because it's like the type of distribution that they follow. Oh, okay. It's just the application itself. So the ideal gas that we have follows the Maxwell distribution, and that's kind of basically stating the number of gas particles. Like if you want to find like the number density of gas particles in this cloud, what is the distribution? Right? So the Maxwell distribution is kind of also called the speed distribution. So it kind of basically is simply it's not normal. What is the exact word for it? Or do we just call it
I think it's like the shape of it is the Maxwell.
It's Bell, but do we just call it?
It's not a bell.
It's not a bell.
No,
it's not a bell. I'm mistaken then.
It looks more like is it like a Rayleigh distribution? Do you know about that?
Yeah, no, I think
it looks more like that, but I don't think like mathematically it's the same.
Rayleigh is more tail heavy, right? Like right skewed.
It is, yeah.
Is that Maxwell? I think Maxwell's no, because RMS, no, Maxwell are kind of right skewed distributions, and again, they're basically just representing like the velocity, like the distribution of the velocities of the different particles, and again, because it's kind of written in classical mechanics, it's treated in one way, which is Maxwell-Boltzmann statistics. Now, in the other situation, when we have the Fermi, it's not called Fermi, that's something else. Fermi is something else, like Fermi energy, that's something else. But it kind of goes into like a fermionic state of gas. Like maybe that's a better word to say, because at the end of the day, all these gases are basically fermions, but we're not treating them like that. Because at this level, when this mean spacing is less than the de Broglie wavelength, we have the Fermi base or the fermions basically dictating with Pauli exclusion principle. So we have these particles that are now coming really, really, really close to each other that are now being kind of repelled, not because of general forces, but simply because of quantum mechanical facts. And which is the Pauli exclusion principle. And this just is a kind of a consequence of when we have our gas either too dense or basically it's no longer ideal. And a lot of cases where we deal with non-ideal gases is where we use I don't really know what it's called. I'm going to call it fermionic gas. I think that's a word for it, but let's call it a fermionic gas. And it kind of represents a little more quantum mechanical state of the gas. So this is kind of just like a preamble to before we really get into the nuclear fusion of it all and really get into the star of it all. Because when we get there, then it's no longer well, it can still be described this way, but then we're kind of looking more at the star and a little more at the fusion, how its, you know, energy is really working, rather than mainly focusing on the gas.